Thank you. Okay, so you've learned that some surfaces can be easily represented by a function of two variables. Like, for instance, a paraboloid, z equals x squared plus y squared. Very easy to graph the surface. Z is a function of x and y. That surface is very nice to represent, as z is a function of x and y. But other surfaces are not easily represented as functions of x and y. And so we're going to use vector functions to discuss more general surfaces that we call parametric surfaces. Okay, so in much the same way that we describe a space curve, okay, let me now try to highlight this and make sure. Okay, in much the same way we describe a space curve by a vector function of a single parameter, like r of t, v of t, a of t, those are space, well, r of t is your founding space curve. But that's a vector function of one parameter. Now we're going to describe a surface by a vector function of two parameters, u and v. Okay, and so this is the format in which we're looking at. And you might wonder, well, how can we describe a surface with a vector function of two variables? I mean, that's a little strange, right? How does that work? How can that be? And the book actually has, I think, a very nice example here, a picture. So what you have is these, I want to say this right, you have parametric equations. The parametric equations are functions of two variables because the vector function is itself a function of two variables. And each point of u and v is going to give a point on your parametric surface S. And by making all the choices, you essentially trace out the entire parametric surface. In other words, this is I'll put this in pink, it's so important. The surface S is traced out by the tip of a position vector as the UV coordinate moves through the region D. So here, okay, here's the region D, and in the plane, the UV plane in figure 1 on the left, the region D is in the UV plane, and UV is a point on that region D. Well, the parametric, the vector function R, that's a function of u and v. Okay, I want to say that again. The vector function R, which depends on u and v, touches a point on the space curve. Okay, so for every value of u and v, for every values of u and v, the vector function touches a point in space. And if you vary u and vary v, you'll trace out a surface in space as you vary u and v. So think of it like using a pencil to scratch out a surface in space. But the tip of the pencil changes as u and v vary. So as u and v vary, the tip of the pencil varies every time touching a new point. All the points collectively in space form the parametric surface S on the right. Okay, are there any questions? Are there any questions on that? We'll look at some examples, but okay, well then let's go down a little bit here. Let's look at example 1. Okay, we say identify and sketch the surface with this vector equation. Okay, that vector equation. Now, you can see below there that they show the parametric equations for the surface. But what helps me a lot, is by holding one of the parameters constant and then varying the other parameter. So for instance, if I were to hold, in this example 1, if I were to hold the V constant, if I were to hold the V constant and let the U parameter vary, okay, then it would make sense to let U vary from 0 to 2 pi. What would that produce? Okay, good, Ryan. It's going to produce a circle. Well, Eric, if V were equal to 0, what plane would the circle lie in? If V were equal to 0, what plane would the circle lie in? It's going to be in the XZ plane. Well, you see the circle the circle is drawn using the I and K vectors, so it's going to be in the XZ plane. Right. Now, what if V were equal to 1? What if V were equal to 1? If we hold that V constant and let U vary, what are you going to get? That's right, Eric. You're going to get a circle at Y equals 1. So at Y equals 1 in three-dimensional space, you're going to draw a circle there. If V equals 2, if you set V equals 2, you'll get another circle. If V equals -2, you'll get another circle. And so you see, by letting the V take on different values, and then just studying what you get, well, I think it's clear that you're going to get a bunch of circles. And the parametric surface is going to be what you see here in figure 2. It's going to make the parametric surface will be a cylinder. That's correct. So the space curve, R of U and V, scratches out a cylinder in three-dimensional space. It scratches out a cylinder in three-dimensional space. Are there any questions on that? You can see it in figure 2. And they make note too that based on the parametric equations here, based on the parametric equations, if you take X and Z and square each of them, you're going to get 4. Okay, so if you square the X and Z components, and add them, you're going to get 4. Okay, and that's the equation of a cylinder whose axis is the y-axis, a cylinder with radius 2 whose axis is the y-axis. Let me see, one moment, class. There is, I think I heard a question here. Yeah, so Eric says, okay, well, what if we were to hold u constant and let the v vary? If you were to hold the u constant, if you were to go back in the back here and instead hold the u constant and let the v vary, it would be kind of difficult to see what you, well, it wouldn't be as clear. So oftentimes when you want to graph a parametric surface, based on your parametric equations, it's often easier to hold one variable constant and let the other variable vary. That's adequate. That's adequate. They also note here that, you know, in this example here, there are no restrictions on u and v. There are no restrictions, okay? But you could put restrictions on u and v. You could say, suppose, let u be between 0 and pi over 2, and let v be between 0 and 3. And if you did that, you would get this quarter cylinder in figure 3. You would get this quarter cylinder in figure 3. Okay, so that's just, you know, so if u is between, like for instance, y is at, you know, y is at the top half there. Well, if we go back to the original vector function, if u is between 0 and pi over 2, okay, that means you're only going to graph, I mean, in order to do a complete circle, you would have to go between what values? What values do you need on u to trace out a complete circle? U has to be between what? 0 and 2 pi. That's right. That's right. That's right, everybody. So restricting u to be between 0 and pi over 2 means you're just going to get a quarter of a circle. But then if you say let v be between 0 and 3, matter of fact, the quarter of the circle is going to be in the first quadrant, right? In terms of the xz plane. And then if you restrict v to be between 0 and 3, that means the y-axis would only go from 0 to 3. So this would be your result. So sometimes you have to put restrictions on your parameters, depending on what surface you're trying to get. And are there any questions on that? Okay. Okay, well, let us continue then. So, okay. They comment here that there are two useful families of curves that lie on your parametric surface. One family where the u is constant and the other where the v is constant. And we just saw that, although in our case it was better to let the v be constant. Okay, and the families correspond to vertical and horizontal lines in the UV plane. You can see this in figure 4. In figure 4, in that region D in the UV plane, the horizontal line, they're letting V be constant and allowing U to vary, and you get that green line. And that green line, those green set of values correspond to curve 1 in the space curve, or in the parametric, no, I'm sorry, it corresponds to C2, that green space curve on the parametric surface on the right. On the other hand, if you were to hold U constant and let V vary, you would get that vertical line segment there in region D, and that would correspond to the red space curve on the parametric surface on the right. You see, when you're holding one variable, one of your parameters constant, your vector function is a function then of just one variable, just like R of t. The vector function R of t was your parameter was t, one variable, traces out a space curve. Well, if you have a vector function of two variables, u and v, but you hold one of the variables constant, then your vector function is really a function of just the one variable. The one variable varies, and so you get these space curves that lie on top of the parametric surface, as seen in figure 4. All right, are there any questions on that? You have to let me know. These are called grid curves, by the way. They talk about it a little bit below the figure. We call the curves grid curves. And, you know, in example 1, the grid curves attained by letting U be constant are horizontal lines, and the grid curves where V were constant were circles. We saw that in example 1. We didn't really explore letting U be constant because, you know, letting V be constant in example 1 allowed us to get circles, and when we put the circles together, we got a cylinder. All right, now, in fact, and this you're going to see shortly, when computing graphs, when a computer graphs a parametric surface, it usually depicts the surface by plotting the grid curves, as we see in the following example. So in example 2, okay, they want you here to use a computer algebra system to graph that surface represented by the parametric surface represented by this vector function. Which grid curves have U constant, which have V constant? Okay, well, so let me ask you, if looking at this vector function, and again, it's usually easier to let one variable constant. If you were to hold the variable V constant, okay, what would that give you? If the variable V were held constant, then the 2 plus sine of V in front of the cosine of U and the sine of U, what would that stand for? What would that represent if the V is constant? The 2 plus sine of V. Well, let me ask you this. The first two, the x and y components, okay, the x and y components, with the cosine of U and the sine of U, what kind of motion does that represent when you have cosine of U and sine of U? Don't worry about the z component. Just focus on the x and y components. The 2 plus sine of v acts as a what? On the, let me see if I can phrase it another way. All right, hang on. Let me go to the board and help you see this. Let's take something. Okay, that's right, Eric. A circle. Let me ask you this. What if you had, hold on here. That's right, Eric. Eric is right. Very good. If you had R of U and V equals, okay, let's write it like this. Let's say you had let's say you had 2 cosine U times I plus 2 sine of U times J plus U times K. Okay. What does that represent? What would this be? Got to be a little careful here. Got to be a little careful because I don't have a V in there. I really want a V in there. But just look at this for a moment. What does this represent? This curve here. Hold on. Actually, hold the phone. I'm not. No. All right. I got. All right. Hold on. I'll do better. Wait. Let's do it this way. Okay. R of t equals. Let's say you have 2 times the cosine of t times I plus 2 times the sine of t times j plus t times k. What space curve is that? Okay, that's right, Alex. Or Ryan, I should say. That's a helix. How many recognize that as a helix? Yeah, what's the radius? What's the radius of the helix? Good, it's 2. And what axis goes through the center of the helix? The x, y, or the z axis? Good, everybody. What center? Good, z axis. Okay, all right. Now, let's alter this a little bit. Let's say you have, maybe I'll put this in red. Let's say now you have a vector function of 2 variables. And you know, all just so I don't have to write I'll use this notation, okay? V times the cosine of U, V times the sine of U, And then hold on here, and then U. Okay, so if V is constant, if we, I want to phrase that another way. If I don't want to touch that button, hold on. I don't want to touch. Okay, if V is held constant, if V is held constant, okay, and let's assume V is positive. If that's true, then R of UV is a blank of blank blank. So if we hold the V, if we hold the V constant, then R of U and V, then R of U and V is a function of one variable, just like up here. If we hold the V constant, R of UV is a what? What would it be? Well, let me ask you this. What's the radius if we hold the V constant? Okay, good, Christopher. Radius V, and what? What of radius V? A, so compare, it's a helix. Good, Jamal, good, Eric. It's a helix. So when you hold the V constant, okay, R of U of V, okay, traces out a helix of radius V. So you get a helix of radius V. Are there any questions on that? All right. Well, what happens then for if you know V's being held constant, but you could change V, right? V could be changed. It could be 1, 2, 3, 4. If you let V equal 1, 2, 3, and 4, how many helices are you going to get? If V is 1, and then 2, and then 3, and then 4, how many helices do you get? Multiple. As a matter of fact, you would get 4 helices, right? So if V is allowed to vary, we're going to get an infinite number of helices. And what would that look like then if we put the helices together? What would that look like? Well, let me show you. Let me show you. Hold on. And in this case, by the way, for example, 2, okay, we don't have a V in front of cosine of U, but we have 2 plus the sine of V. And if V is constant, that's just some constant. Similarly, in front of the sine of U, if if V is constant, 2 plus sine of V is going to be some constant, and it'll be positive, by the way, because the sine of V is always between 1 and -1. So it acts like a radii, right? All right, and then the third component, U plus cosine of V. Well, if cosine of V is constant, you still are going to have something that changes with U. So if you put everything together, you're going to get figure 5. You're going to get figure 5 here. You see the grid lines where V is held constant? You see the grid lines? The two grid lines? For different values of V, you get different helices, and if you put the helices together, it's going to trace out that figure that you see right there, that parametric surface. Well, Eric, and we're going to go to MATLAB. We're going to go to MATLAB, but let me ask you this. The helix, or this parametric surface. I want to say this the right way. What they're saying is in the problem here, they're going to graph a portion of the surface where they're letting U be between 0 and 4 pi. So that'll trace out two revolutions of the 2 revolutions, and V is between 0 and 2 pi. Okay, so they're restricting V so that your radius is restricted. But do you see that essentially you're concatenating, you're putting together, like think of string, think of like I don't know, like how many have seen like a blanket with like, I'm trying to think of the right thing. I don't want to think of patches, but just think of taking a bunch of helices with different radii and gluing them together. You see, you would get something that would look like that in figure 5, a parametric surface that would look like that. Does it make sense that the grid where it says V is constant, does it make sense the 2 arrows where V is constant, how it's as you vary V, you're tracing out a helix? As you hold V constant and let U change, you're tracing out a helix. And then as you change the value of V, you trace out different helices, and you glue them all together. You get that parametric surface there. Okay, good. I was hoping, of course we can go to MATLAB and graph this parametric surface, but it's not going to give you insight into why the surface is the way it is. So we need to have just a little intuitive feel before we go to MATLAB. But on that note, let me go ahead here and let me go into MATLAB, or I'm sorry, go into Blackboard. So what I'd like you to do here is let me bring up the Blackboard. Okay, can everyone see Blackboard okay? In the window here? Okay, thank you. Thank you. Okay, so you go to MATLAB Programs. Click here, Helpful MATLAB Programs. And right here we have section 10.5, Parametric Surfaces. this MATLAB program will help you draw parametric surfaces. So I'm going to click on the MATLAB program link, and then I will open up, download the program, open up the program, and it will bring you, hold on here, I just want to get rid of the junk here. Yeah, let me go back in here. Hold on. Now I want to go into MATLAB. Let me do CLC. Incidentally, what I should do too, I mean, you can do this in the programs. You can do something called clear vars. Okay, clear vars, clear variables. I'll do a save here. Well, no, I'll just clear variables. What that command does is, like, if you have any old variables in your workspace on the left, it'll clean those out to make room for the new fresh variables. And I think it's helpful to do that, to use that command. How many have heard of that command in MATLAB? Clear vars for clear variables. Has anybody seen that before? Okay, Eric's seen it. All right, all right. And Robin's seen it, and Nema. Okay, great, great. Well, all right. So now I'm going to copy. Oh yeah, let me make a comment here. So here you have to divide your symbolic variables u and v. Those are your parameters. And I have x, y, and z here. And I'm using the EasySurf command as shown. But 0 and 4 pi, okay, that stands for let v be between 0 and 4, or let u be between 0 and 4 pi, and then the next 0 to 4 pi means let the parameter v be between 0 and 4 pi. Okay, but what I could do, I guess, is they're letting u be between 0 and 4 pi, but they're letting v be between 0 and 2 pi. So I'll do that, okay? I'll do that, and let me do a save on that. Okay, and let me, hold on, there was something in the chat here before I graph it. Something in the chat. Okay, very good, very good. Let me go and paste this on the command line and hit enter. And it produces a figure. So let me get the figure here. Okay, there you go. All right, and you can go to Tools, and you can go to Rotate 3D if you want to rotate it a little bit. And of course, the X and Y axis, we can get them the way we're used to. You just have to turn it around. But how many think this is pretty cool? Jamal likes it. All right, and I'm getting a lot of, I can't see your names because on my screen the one figure's blocking it, but there you go. Now there's going to be a matching problem in your section 10.5 homework, which you'll that'll be due for Thursday. You'll have a chance to use this program, but the matching problems, it might be a little more fun to try to not use MATLAB and just like hold one of your parameters constant and then study what grid curves you get. What grid curves you get. Okay, I mean, isn't that more fun than just using MATLAB? I don't know. Wouldn't that be a little more fun? I'm not sure. How many want to use the MATLAB? code and just play with that. Well, you know, I'll leave that up to you. But that being said, let's talk a little bit more about section 2.5 here. So we go back to the book, and we continue here. So, okay, let's move on. So parametric equations for a plane. Okay, so how do we get parametric equations for a plane? Well, you've already seen what parametric equations for a plane look like, but in figure 6, what they do is they have an equation of a plane, and they say, okay, if we have a point on the plane, p sub 0, and we want to locate another point, p, on the plane, well, if we had two vectors, a and b, in the plane, and we took a linear combination of a and b, if we went u times the vector a and b and v times the vector b, for appropriate values of u and v, we could locate that point p in the plane. And so therefore the parametric equations for a plane in example 5 can be just represented this way. Some initial point r sub 0 plus the vector u times a plus the vector v times b. And a and b, those vectors have to be in the plane. And that's how you parameterize a parametric. That's the parametric surface. If it's a plane, it's going to follow that form of that vector function of u and v. Okay. All right. So far, so good. All right. Well, let's look at parameterizing a sphere. Okay. Here's a sphere. How would you parameterize a sphere? Well, you already know. Hold on. Now I lost the. Hold on. I don't know why the book just kind of disappears on me. I don't understand it. But all right. Let's continue here. Did I get through the previous example okay? Example 3, or did that like get through all right? Okay, good. I'm gonna have to. I think what it is. Thank you, Robin. Thank you, Diadath. I think it's kind of maybe it's a security feature. Excellent. Maybe a security feature for the ebook. I don't know, but you know. One challenge at a time, right? All right, so here we want to parameterize a sphere. So a sphere, as you know from section 9.7, when you learned about spherical coordinates, the x, y, and z components for a well, I want to say this the right way. If we want to convert from Cartesian coordinates or rectangular coordinates to spherical coordinates and back, these are the three equations, x, y, and z equations, that are your conversion equations. They're the parametric equations for, well, those are your conversion equations. And if we're going to let the angles phi and theta, if we're going to let them be your parameters, okay, then this would be your function of your parameters. This would trace out a sphere. As you vary phi and you vary theta, and a, of course, it's the radius of the sphere. If you vary phi and theta, You'll scratch out a sphere. You'll scratch out a sphere. They have a little picture here. In figure 7. Okay, there's a sphere. There's a sphere. And look at when you hold, well, when theta equals, well, let's look at phi equals c. So the angle phi is measured from the positive z-axis. But if you hold phi constant and you let theta vary, you know, theta is your angle measured, you know, from the positive x-axis. Phi equals c is just going to be that curve, that red curve. So phi equals c means you let theta vary, but you hold phi constant. On the other hand, theta equals k. If you hold your theta constant and then let phi vary, you're going to get just the front part. You see that blue space curve there in figure 7? Okay, I mean, what I'm trying to do here, I'm trying to get it the best I can. In figure 7, okay, figure 7, the blue space curve, the blue grid line, or I should say the blue grid curve corresponding to theta equals k, does that blue grid curve look like it goes all the way around the sphere, that blue grid curve? The red grid curve forms a complete horizontal circle. Okay, and that makes sense because theta can go from 0 to 2 pi. And that parameter can go from 0 to 2 pi in spherical coordinates. But the blue curve corresponding to the grid curve theta equals k, does that blue curve go all the way around the sphere? Yeah, to me, it looks like it does not. I agree with Jamal and Diodath, and in fact, they are right. Why? Okay, so Jamal's saying that it goes from the positive z-axis down to the negative z-axis, but it doesn't go any further. It goes from theta equals, well, on the positive z-axis, on the positive z-axis, what is phi equal to? Phi is equal to what? Think of your spherical coordinates, positive z-axis, phi, at the positive z-axis, phi is equal to what? Phi is measured from the positive z-axis. So if you're on the positive z-axis, what's your value of phi? Well, phi equals pi over 2 would put you in the xy plane. That's 90 degrees. But, right, the good area, 0. But then, so remember, let me go to the board here. Hold on. Okay. Hold on one moment. Good. I didn't see that last response, but one moment. So if we think about the z-axis, okay, here's the origin. Here's the origin, okay. And if we measure like this here, what's phi equal to here? What's that angle? Well, hold on. Yeah, this angle here is phi equals what? Let's do the red angle. That's probably the easiest. Okay, 90 degrees, pi over 2. Okay, it probably would help if I drew, but put it in black for goodness sake, or maybe I don't know, maybe purple. Okay, there's phi equals pi over 2. Then the blue angle is going to be phi equals what? Pi over 4. Good. Okay, let me do a green angle. Okay, what's phi equal to for the green angle? Good, 180 degrees. And for spherical coordinates, you remember that phi is restricted between 0 degrees and 180 degrees. Okay, phi is between 0 degrees and 180 degrees. So then, if we go to that picture, this blue ball here, the blue grid curve, where theta equals k. Theta equals k means you're holding your theta angle constant, but you're letting phi vary. So I'll ask you then, is that blue grid curve corresponding to theta equals k in this figure 7, does that blue grid curve go all the way around or just halfway around? Halfway around. Good, good, good. That's what. So I'm trying to give you an intuitive. Was this helpful to give you a little bit of an intuitive feel? Was this helpful? Okay, good, good. Excellent. Thank you, Deoda. Thank you, Robin. All right, all right. So let's look at a few other examples. Let's look at a few Dr. Duty examples here. Let me bring them up. Okay, and I think the first one, I'll do this one first. Okay. Okay, so take a moment and copy this example down. All right. Okay, so let's take a look here at what we have. So we want to find the parametric representation for part of the sphere that lies between these two planes, the plane z equals 2 and z equals -2. What's the radius, by the way, of this sphere? What's the radius? 4. Okay, good. What would maybe be helpful in this problem to, give us a little bit of a feel, intuitive feel? What might be helpful? A drawing. I agree. Good, Diadath. Good, Air. Good, Ryan. Yeah. And so that's what we're going to do. So what I'm going to do when I go to the solution here is I have here a little picture, and I did this problem just like a student would, and I drew a little picture, and I note, incidentally, that for this sphere the radius is 4, so that just stays there. But these are the parametric equations, the x, y, z components for a vector function with parameters theta and phi. And on the right here, I draw a circle, a sphere, I should say, with radius 4, and I draw a couple of planes that cut through the sphere. And it makes sense the planes would cut through that sphere because the sphere has radius 4. So those planes z equals 2, z equals -2 are gonna cut through that sphere. What plane, incidentally, what plane would hit the sphere right at the tip, right there? What plane would hit the sphere right there? What plane would be tangent to the sphere right at that point? Z equals 4. Good. That's right, Robin. Z equals 4. Okay. All right. So, well, first of all, the intersection, well, no, let me give you a moment to, I'll give you a moment to catch up here. Let me know if you have any questions. Okay, so the intersection of the plane z equals 2 with the sphere, well, I'm going to substitute in for z equals 2. And that's going to get me 1/2 equals cosine of phi. And so, well, phi is going to equal pi over 3. And if you look right, let me see here. This is, got to be a little careful here. The picture's not exactly drawn to scale, but if you let me see here. The cut of the sphere is going to trace out a, it's going to trace out a circle. And if phi measured to that circle would be pi over 3. It's not, picture's not exactly drawn to scale, but and then the intersection of the plane z equals 2 with the sphere would yield phi, well, cosine of phi would equal -1/2. And so phi equals 2 pi over 3. Now, pi over 3 is 60 degrees. How many degrees is 2 pi over 3? (120 degrees). So does it make sense? Does it make sense based on the picture then that, down here, if I, hold on, let me erase here, hold on. If I were to just, draw, man, I can never get this. If I were to just kind of, draw that there, okay, where the sphere intersects the plane, and think about the positive z-axis, there it is, positive z-axis, right there, and measure the angle phi from the positive z-axis to there. Would it make sense that phi equals 120 degrees, or 2 pi over 3? Would that make good sense? There you go. There you go. But remember what we're looking for here in this problem. Remember what we're looking for. Okay. We want a parametric representation for the part of the sphere that lies between the planes. So that means we want the part of the sphere that is this part of the sphere, right? Maybe I'm putting it in green. Well, it's this part of the sphere here. Right? Maybe I don't need, hold on, we don't want, hold on here. I mean, I can do, I mean, hold on, class. Hold on. You see what I'm trying to do, right? You see what I'm trying to do. I'm drawing. So that part of the sphere, the surface would be described here. And actually, hold on. This should be 2 pi over 3 here. It's not a cylinder, Jamal. It's not a cylinder. It's like a part of a pumpkin. Think of a pumpkin. Think of taking a pumpkin and chopping off the top part of a pumpkin, like slicing it horizontally, top portion of the pumpkin and bottom portion of the pumpkin. It's this is what it looks like. That's what you got. It's the this is the but that's your surface. That's your surface. And hold on. Yeah, I did. Phi is between 60 degrees and 120 degrees, and theta is 0 to 2 pi. Does that help you see it, Jamal? Are you? This is what the surface would be described by those equations there. So you see, that's how you can describe the surface that way. Okay, excellent, excellent. Are there any other questions on that? We're going to do one more example before I have you work. We probably won't be as much time tonight to work on the 10-point, but I'll do the best I can. Any questions before we move on? Okay, all right, very good. Well, then let me go back. Let's look at this problem here. Okay. All right, let me give you a moment to copy this example down. Incidentally, a lot of these type problems in WebAssign are, there's multiple choice or multiple choice portions. So I want you to, I'm trying to cover a variety of examples so that, you don't want to answer multiple choice questions too quickly, right? Pretend it's an exam, right? Try to get it right on your first try, right? But, let me give you time to copy this example down and we'll go over it. Okay, so here we want to find the parametric, let me put this maybe in blue. We want to find the parametric representation for the surface described by this sphere. What's the radius of this sphere, by the way? Good, the radius is 10. So we want to find the parametric representation of the surface described by this part of the sphere, radius 10, that lies above a cone, that lies above this cone. Okay, so the normal equation for a cone, well, the standard form of a cone is if you look back in, hold on, this was section 9.6. The standard form of a cone is z squared over c squared equals x squared over a squared plus y squared over b squared. Okay, and of course, if like in this case here, like for this one, well, if A, B, and C were equal to 1, okay, if A, B, and C were equal to 1, you'd have, z squared, if A equals B equals C, and they're all equal to 1, then z squared will equal x squared plus y squared. Now, this here is the equation of a cone that you would see in section 9.6. So what did they do here? They're calling z equals the square root of x squared plus y squared the equation of they're calling that a cone. Okay. So what did they do to our standard, to this equation of a cone? What did they do to both sides? To get here, they're good. They took the square root of both sides of that equation. Well, shouldn't I have but I don't have a plus or minus square root. I just have a plus square root. So would that be a top half of a cone? Remember a cone, how it looks. Would that be the top half of a cone or the bottom half of the cone? Okay, well, that's right, Ryan, the top half. Okay, so, just kind of, all right, let's go ahead then. Are there any questions before we move forward? Okay, well, let's move forward then. I've drawn a picture of the here's the cone right here, and then the sphere. The sphere, of course, was x squared plus y squared plus z squared equals 100, but z equals positive square root of 100 minus x squared minus y squared would represent the part of the sphere that, well, I want to say this right. Technically, the sphere should continue, right? And I'm sorry it isn't the perfect drawing, but technically the top half of the sphere would go all the way down to the XY plane, right? But we only care about the part of the sphere that's above the cone. So that's this part. And I know this isn't exactly, it's not exactly drawn correct here. It should be, this should be more of an angle, like more of an angle. You know, that's like an angle there. Okay, more of an angle, but it's fine. It's fine. So we need to determine then, hold on. One moment. Okay, hold on. One moment. Yeah, okay. So, all right. What I'm going to do is I'm going to use parameters x and z, or x and y. Okay, I'm going to use parameters x and y instead of like a sphere. The last example, we used parameters theta and phi. But now I'm going to use parameters x and y. So clearly, if I'm interested in this shaded area here, you know, I'm interested in that shaded area, it's very important to identify where the cone intersects the sphere. And so for that, I have to set the the equation of the sphere equal to the equation of the cone. I'm saying, you know, z equals z, okay, where the cone, the z coordinates, equal the z coordinates of the sphere is where the intersection is going to be between the sphere and the cone. Um, right, right. And so now what I do is I work this out, and I get x squared plus y squared equals 50. So if I were to take the blue circle of intersection and project it down into the, let me just hold on, erase here. If I were to take this blue circle of intersection and project it down into the xy plane, for every point, well, I want to be a little bit careful. I don't really need to do that. No, I don't really need to do that. I don't need to do that. Let's just focus here. You know, let's not make things difficult. This is the blue curve that represents the intersection of the sphere and the cone. Well, when we set the equations of the sphere and the cone equal to each other, we're saying, hey, find the x and y values that will satisfy that curve of intersection. And it turns out that 50 equals x squared plus y squared. The x and y values that satisfy this equation are the coordinates of the points that lie on the intersection of the sphere and the cone. Incidentally, the x and the y satisfy x squared plus y squared equals 50 but the z coordinate would have to be the square root of 50. Okay, so I think that I felt very clear when I wrote that out. Are you comfortable with that? Are you comfortable with this statement here? Are there any questions on that? Ryan's good. Deodath's good. Wonderful. Jamal's good. Excellent. Well, then, you know, the space curve, or no, not the space curve, the vector function that's going to describe the vector function of parameters x and y, that's going to give this shaded parametric surface of interest is given here. R of xy is x, y, and then z is the square root of 100 minus x squared minus y squared. But the restriction is that x squared plus y squared has to be less than or equal to 50. Because equaling 50 will just give you this rim here. It'll give you the rim. But we want all the little points. You know, we want all the x and y points. We also, to get the shaded area, we need x squared plus y squared to be less than or equal to 50. Okay, so sometimes, you know, I don't want to say too much. I want to say enough, but sometimes saying too much may not be helpful also. You know, are we okay with what you see here? Let me know if you have any questions. Okay, Eric's good. Okay, now this was one way to do this. Okay, here, this way, we used parameters x and y. Those were our parameters. But could we do this problem with parameters theta and phi? I mean, it might seem natural we could. After all, there is a sphere involved here. Let me show you how to do it a second way, a second method. May I go to the next page? All right, all right. Okay, then to the next page. Second approach would be this. Your parameters are theta and phi, and this is your vector function. So in this case, it was easy to get the vector function because we know that we know based on the picture, okay, that the parametric surface S here, this parametric surface lies on the sphere. It lies on the sphere, right? I mean, it is part, it is, I should say that another way. The parametric surface, the shaded surface, is part of the sphere. So the parametric equations must satisfy a sphere. And you learned from spherical coordinates, section 9.7, how to define x, y, and z. So in that case, it was easy to get the components, the x, y, and z components. Where the work comes in here, though, is to figure out what the restrictions are on theta and phi. Well, theta is just going to go from 0 to 2 pi. You need a complete revolution to capture that top piece of the sphere. But phi is going to be between 0 and pi over 4. Okay, the question is why? Well, to see the restrictions on phi, okay, here is the justification. Let me give you a moment to catch up here. Okay, so for the justification, okay, remember, let me go back to the picture. I'll come back. Remember, phi is measured, hold on. Phi is measured from the z-axis. And that's why I was saying, technically, my picture, technically, my picture, hold on here. Let me just try to get this. So technically, the picture should look more like this. Okay, the shaded area or the shaded surface should look more like this. Doing the best I can here. Okay, it should look more like, well, more like that. But let's just proceed on here. It's fine. Let's just proceed on. So to get the restrictions on phi, we recognize that where phi is going to be measured from 0 degrees all the way down to the, I'm not saying this the right way. I'm sorry, let me, I mean, I know what I want to say. I just got to say it the right way. So this here, okay, if we look at the angle, if we just look at the angle here, we just look at phi. So this top point here, what would phi equal for this top point of the surface? What's phi equal to? Phi is measured from the positive z-axis. Yeah, phi equals 0. Okay. And let me adjust my picture. I think I got this now a little bit better. Okay, I'm gonna make my cone more like that. I'm sorry, class, I gotta do this. I have no choice, all right? I don't even know if I can, let me just draw a little bit better picture here on the right. I wanna do this, I wanna do this. I wanna do this properly. So, okay. Okay, so kind of like that. All right. Here's the z-axis. Okay, so here, okay, phi equals 0. What about here? I tell you what, let me just go with this picture, okay? And I'm gonna just keep it simple, okay? So the point is, we got to get a restriction on what phi is, okay? Phi would end, measuring the phi from the positive z-axis, phi would end at the cone, where the cone touches the sphere. So if we figure out what the equation is for if we figure out the boundary for the cone in terms of phi, we'll get the ending angle. And so what I do is I put in the definition for z, x, and y, and I write the equation of the cone as an equation of the cone in spherical coordinates. So the equation of the cone in spherical coordinates is phi equals pi over 4. Okay, phi equals pi over 4. And therefore, when phi is between 0 and pi over 4, that's going to give you the desired points. That's going to give you the part, that's going to be the restriction on the angle phi that will give you the top portion of that sphere. And what I'll do is maybe while you're working on your classwork, I'll try to draw a little better picture on the whiteboard. But generally, are you okay with what? Are you okay with this? Are there any questions on that? All right. Let me stop the recording.